All right, looks like we are ready and set up for our live stream tonight. Tonight, I think the focus is going to be on working through some calculus questions for your calculus midterm tomorrow. So let's see what we got going here. Yes. Okay, now I'm fucking ready to do some calculus. Okay, let's start with some limits. Just to get us warmed up, let's take a look at this first one. First one is the limit as x gets closer to 3 of the function 1 over x minus 3 all squared. So kind of first things first, I want to work through a direct substitution, and I want to see what's going to happen when I do a direct substitution. So in blue here, I'm just going to say, okay, well, I'm going to get 1 over 0 squared, or 1 over 0 when I do my direct substitution. That's going to give me some information about how to tackle this particular limit. So this function actually has a vertical asymptote at x is equal to 3. So I know that if this limit exists, it's going to be either plus or minus infinity. The limit may not exist because one side may go to positive infinity, the other side may go to negative infinity. So we'll have to figure out our two one-sided limits and see what's going on with that. So underneath, I'm going to start by working through the limit as x goes towards 3 from the right of this function. So I'm going to take my calculator and I'm going to substitute in a value that's a little bit bigger than 3 and see what's going on. So I get 1 divided by maybe something like 3.1 minus 3, and that gives me 10. So like I said, I'm kind of trying like values like 3.1, 3.01, 3.001, and I'm trying to see if there's a pattern in the output values or the y sequence that I'm getting. And it looks like they're getting bigger and bigger and bigger, so I can comfortably say that this one's tending towards positive infinity. And if you do check the other sides, if you do check the limit as x gets closer to 3 from the left, so thinking about values like 2.9, 2.99, 2.999, and taking a look at that sequence of y values that pops out. Because the denominator is squared, you're going to end up with positive infinity from the smaller side of 3 as well. So since our two one-sided limits are tending towards the same value, this vertical asymptote is going to tend towards positive infinity from both sides. So we can, this limit technically really doesn't exist, but we're going to say that it does get unbounded as we get closer and closer to 3. And if you do want to just double check this, you can plot it into Desmos. So 1 over x minus 3 squared, and there it is. So as we get closer and closer to 3, our limits are telling us that that vertical asymptote right at x equals 3 on either side is blowing up and going towards positive infinity. Okay, so that's how we tackle that first limit. Remember, if you do have some questions that are kind of popping up tonight, and you would like them solved, just send them to mathquestionshelp@gmail.com, or feel free to kind of drop something into the chat as well. I'll be kind of peering in at that periodically to see if anything exciting is happening in the chat. So let's kind of continue on through a couple more kind of warm-up limits, and then we'll get to working through some of the questions on the practice test. By the way, the first 3 limits that we're working on tonight are brought to you by Moon Cursor, or Carmenaire. It's a lovely red one. No, I'm just kidding. I'm not sponsored. Sponsor me. But yeah, it's delicious. And yes, I do have a bottle of wine in my office. Please don't judge me. Okay, so next up, let's look at a limit as x is tending towards an infinity. So we're going to look at a limit as x is getting either really, really big, or in this case, really, really big and negative. So the standard method of attack when x is tending towards either positive or negative infinity is to divide every term by the highest power of x in the denominator. So the highest power of x in the denominator here is x to the 3. So I'm going to divide all of my terms by x to the 3 and simplify and see what happens. Okay, let's just simplify a couple terms here. And now we should be in a good spot to consider what's happening as we get really, really big and negative. So as x gets really, really big and negative, anything that's going to have an x in the denominator is going to tend towards 0. So all of these in blue are going to tend towards 0. So we're going to be left with 0 over 1, which is 0. All right, so next up, let's take a look at one final warm-up limit here, and then we'll start working on some of the harder questions, I think, from the practice test. So here, let's look at a limit as x gets closer to 2 of a subtraction of 2 fractions. So what I might do here is I might start working on getting a common denominator for these fractions. If I can get a common denominator, I might be able to combine them into one big overall fraction, and maybe some stuff's going to cancel. So let's take a peek at that. In blue, I'm going to go ahead and factor this as x minus 2x plus 2. So that's actually going to be the common denominator that we want. So that means that this fraction over here has to be multiplied by x plus 2 over x plus 2. Okay, so my first fraction is going to now look like this. And my second fraction looks something like this. And let's go ahead and combine those. So we have limit as x gets closer to 2, x plus 2 minus 1. So x plus 1 in the numerator, and x minus 2x plus 2 in the denominator. Darn, I was kind of secretly hoping that something was going to cancel for us. I'm going to make this limit a little bit easier to work with. Because right now, if I go and do, or try to do direct substitution, I'm going to get 2 plus 1, which gives me a 3 in the numerator. And I'm going to get a 0 down here in the denominator. So essentially, this is telling me that this function has a vertical asymptote at 2. So our final answer, if we can write something down for our limit, is going to be plus or minus infinity. So we're going to have to go through this process of taking a look at the limit as x gets close to 2 from the right, as well as the limit as x gets close to 2 from the left. So let's go ahead and try that. Okay, so for this one here, maybe try some values like 2.1, 2.01, and you want to try to get a sense of what's happening to those y values. Are they blowing up to positive infinity, or are they getting really, really big and negative and tending towards negative infinity? So let's take a look. Our numerator is always going to be positive, and for values a bit bigger than 2, so I think if you toss some numbers into your calculator, you should get positive infinity here. Okay, and you want to do the same kind of thing for values a little bit smaller than 2, like 1.9, 1.99, and see what's happening there. And let's see if I can kind of reason through this. So positive, that's going to be negative. So I think this one's going to tend towards minus infinity. So what does that tell me? That tells me that my two one-sided limits aren't the same. So around this vertical asymptote, it really doesn't make sense for us to talk about the limit. We're going to say that this limit does not exist. Okay, and if you do want to quickly see what that function looks like in Desmos, we can go ahead and plot that. So what do we have? We have x plus 1 in the numerator, x minus 2, and x plus 2 in the denominator, and we were looking at x equals to 2. So I'm just going to put that in red as our vertical asymptote. So you can see that as we get close to 2 from the right-hand side, it's blowing up towards positive infinity, and as we approach 2 from the left-hand side, it's getting really, really big and negative. So overall, this limit, it doesn't make sense to either say positive or minus infinity. It just doesn't exist here at this vertical asymptote. All right, so how are those warm-up questions? They are pretty intense, eh? Not too bad. So if you guys are putting in, at least a couple hours of studying time, that would be great. I had to go to the dentist today, and they had to fix 3 cavities. Oh my gosh, like I can still hear the drilling in my face. It was brutal. All right, so for those of you that are just tuning in, if you do have some questions that you do want answered, send your questions to mathquestionshelp@gmail.com, or let me know in the chat if there maybe, for example, there's a specific question on the practice test that you do want to do, and I will go over that. I did have a request to look at question 5 from the practice test, and that is using the squeeze theorem. So looking to show that the limit as x gets closer to 0 of this function is 0. Okay, so if you are going to use a squeeze theorem thing to prove a limit, chances are you want to start with something that has an inequality. So the inequality could be given to you in the question, like some of our homework questions if you looked at the live stream last week, or you may have to make it up depending on the limit that you're working with. So for us, we're going to have to make it up because it's not given to us, and we're going to start with something that we know. So for example, if I go and I plot cosine of x in the xy plane, I know that the smallest y value is -1, and the largest y value is +1. Okay, so cosine is always going to be in between -1 and +1. Ali, yes, absolutely. We can work through the last 2 questions on the practice test for sure. So I'm going to work through 5 first, and yeah, then we got some free time, so I'll kind of play around with some of the questions that you guys want answered from the practice test. So returning just back to this squeeze theorem limit just for a second, we know that cosine is between -1 and 1. If I go ahead and alter the inside of this function, so changing this to cosine 1 over x, what's this going to do to the outside values? Well, it turns out that if we change the inside part of this function, nothing's really going to change. And hopefully you can kind of convince yourself by either plotting this in Desmos or just kind of knowing that when I do some action inside of the cosine function, it doesn't change the y values. So it changes the period in some sense. It kind of really crunches everything close to 0. But notice that my smallest y value is still -1 and my largest y value is still +1. Okay, so next up, I want to try to get this entire function bounded between some stuff. So I'd like to know where this function is bounded between, like, so what's its upper bound and what's its lower bound. And it turns out it's going to be bounded above by x squared, and it's going to be bounded below by -x squared. So all I've really done as I move from here to here is I multiplied everything by x squared. Okay, and once again, I'll try to show you a visual of what that looks like on Desmos. So we'll take this cosine function, we're going to multiply it by x squared. I'm going to zoom in a little bit so you can kind of see that it's this kind of creepy parabola looking thing. Oops. And then we'll plot a parabola x squared, and we'll plot the parabola -x squared. I'm going to maybe put that in black as well. Okay, so you can see kind of anywhere, if I zoom in a little bit, my red function is always bounded above by x squared and always bounded below by -x squared. So that's kind of cool. And what we're going to try to show is as we get closer and closer to 0, right, you can see that this red function is getting squeezed into y equals 0. So its limit as I get closer to x equals 0 is going to be y equals 0. Okay, so now let's try to figure out the limit of this function as we get close to 0. It's going to be bounded above by whatever the limit of this function is. And it's going to be bounded below by the limit of -x squared as we get close to 0. And we happen to know these two limits. Like, I know what this limit is. I can just do direct substitution. This limit is 0. I know this limit. That's just a nice continuous parabola. So if I sub x equals 0 in, I will get 0. So the limit of our function, it must be equal to 0 as I get really close to 0, because from above, I'm getting squeezed to 0, and from below, I'm also getting squeezed to 0. Okay, so that's kind of the idea. If you are given a function and you're not given bounds, the first thing you want to do is try to kind of figure out some upper and lower bounds. So for example, if you're working with sine or cosine, you know that cosine's always never going to be bigger than 1 and always going to be bigger than -1. Okay, and then these next couple steps is just trying to build this function. So I'm trying to alter my original inequality to get what I want. So notice that these two pieces are the same. Now, and then kind of your last step is to apply the limits and pray to the calculus gods that both of those limits on either side, the right-hand side and left-hand side, tend towards the number that you want. So hopefully that gives you kind of a breakdown of a squeeze theorem type question. So let me know if you have any questions about that one. I was asked to take a look at question 1c. So 1c is if we have the function 1 over x. We want to figure out what f at x plus 2 looks like, and then try to find the difference quotient. So we'll do the difference quotient after we get f at x plus 2. F at x plus 2 is going to be a fraction that looks like this. Okay, so everywhere I see x in my original function, I'm going to substitute in x plus 2. And then the second step is to look at this difference quotient, so something that we might see when we're going to find the derivative, for example, and simplify this as best as we can. So f at x plus 2 is this one, f of x is this one, and all of this is divided by 2. So here I'm going to maybe try to give you a tip or a way to think about this kind of simplification. To be honest, I really dislike this second division bar. Like, I really hate the second fraction bar here. So if there's too many fraction bars here and it's helpful to rewrite this in a different way, then do it. I tend to prefer to look at this like 1 over x plus 2 minus 1 over x, all divided by 2. So I'm kind of changing this fraction bar that I've highlighted into a division symbol, just so it looks a little bit nicer, it looks a little bit cleaner, and I don't lose that kind of extra division step along the way. So what we want to do next is try to find a common denominator here for our simplification. So x plus 2 and x don't share any factors, so the best I can do is multiply this first fraction by x over x, and multiply my second fraction by x plus 2 over x plus 2. Okay, so here we have our common denominator. So let's go ahead and just simplify or subtract those fractions. Notice that our x parts are going to subtract to give me 0. So my numerator, I'm going to be left with 2. So I'm going to have 2 over x plus 2. I apologize. It actually should be negative 2 over x times x plus 2, and that's because this minus sign has to distribute to both the x and the plus 2. So yeah, this numerator should be negative 2, and then I still need to divide by 2. Okay, remember that dividing by 2 is really the same thing as multiplying by 1/2. Okay, so I'm thinking about this fraction up here as 2 over 1, and then I'm going to flip that fraction, multiply by the reciprocal, and we're going to end up actually dividing out these 2's. So our final simplified answer should be negative 1 over x times x plus 2. All right, so let's see what is up next. So that is 3, oh no, that was 1, right? 1C. I was also asked to do a little algebra work here with 3A. So this is determining the composite function given to other functions. So let's say I have a function x, and I have a function g. We would like to find the composite function and then simplify as much as we can. So let's look for f composed with g. So remember that f composed with g is really just saying, like, take the function f, and then you're going to substitute g of x into f. Or in other words, anywhere I see x up here, so like here and here, I'm going to substitute in g of x. So I'm going to get g of x plus 1 over g of x. Okay, we know what g of x looks like. G of x is x plus 1 over x plus 2. Now we have something kind of similar to the last question we were looking at pop up here. We have two fraction bars over here, and kind of this top one's really bugging me. I'm going to try to get rid of this top fraction bar by thinking about this as 1 divided by x plus 1 over x plus 2. So this is really kind of like 1 times x plus 2 over x plus 1. So we can simplify this to x plus 1 over x plus 2 plus x plus 2 over x plus 1. Okay, so all of that work is just kind of done over here, and then this becomes my new piece down here. So that just kind of gets rid of that ugly looking fraction over on the right hand side. And now it really just becomes an algebra problem. Can I add these two fractions together and find a common denominator? So our common denominator here is going to be x plus 1 times x plus 2. And it looks like our first fraction was missing an x plus 1, and our second fraction was missing an x plus 2. So let's go ahead and expand out this numerator and see what it looks like. So x squared plus 2x plus 1, and x squared plus 4x plus 4. If you've watched some of the other live streams, you know that I tend to leave my denominators in factored form. So my preference here is not going to be to expand the denominator, just in case something's going to cancel. So yeah, so I'm just going to leave that as x plus 1, x plus 2. It doesn't look like really anything too exciting is going to happen up top, but I'll just kind of combine some stuff anyway. So 6x plus 5. I don't know if that first one's going to factor. We could use our calculator to see if it's going to factor into something nicely. If it doesn't, I wouldn't worry too much about it. If you do want to know how to check to see if it factors, just use the quadratic equation. And if we get some solutions, then it is going to factor. So on our calculator, it would be mode 5. That gets us into equation mode. And then 3 is the quadratic equation solver. And I'm just going to toss A, B, and C in. So here A equals 2, B equals 6, C equals 5. Yeah, and it does factor, but it only factors over the imaginary numbers. So my numerator is not going to factor. It's called an irreducible quadratic. I'll talk about that more next semester. So this is pretty much as good as it's going to get. So this is the simplified form of f composed with g. If you did happen to expand out the denominator to get something like x squared plus 3x plus 2, that's fine. I would mark that as completely right. But like I said, I just tend to favor having a factor denominator. Just for most calculus applications. All right, so let me know if you do have any questions about that process. If something kind of didn't make sense, just let me know in the chat, and I'll see if I can come back to that and kind of point out some extra info about that. So for those of you, again, if you're just kind of tuning in and you want to send some questions for me to go through, feel free to send them to that Gmail account. And I have just a couple more questions to look at on the practice test. So Ali wants me to take a look at question 7D. Let's see what's in there. Oh, yeah, these awful limit questions. Oh, yeah. I'm surprised no one's asked earlier about these awful limit questions, Ali. Okay. So just let me copy these down. So as x tends towards 0 of arctan 1 over x. Oof, that sounds not pleasant at all. Okay. Wow. What do we do here? Okay, this is not looking good. 1 over x is not particularly pleasant. Okay. So if I go to do a direct substitution, I'm going to get arctan, or tan inverse, of 1 over 0. So something really funky is happening at 0. Maybe a vertical asymptote, or maybe it's getting kind of crunched, like we've seen cosine of 1 over x do. So if I kind of come back here to Desmos, cosine of 1 over x looks just super funky as we get close to the origin. Okay, so here's cosine of 1 over x. So maybe arctan's doing something kind of similar. It's getting kind of crunched as we get closer and closer to 0. I don't really know. So let's try to figure out algebraically what's happening. And we can do that, hopefully, by trying to consider two limits. So let's try the limit as x gets close to 0 from the right, and the limit as x gets close to 0 from the left. So here, yeah, maybe we'll have to do a table of values. But that's okay. I mean, it's kind of annoying to have to do it, but it hopefully will give us some information about what's happening with this function. So let's take some values. A little bit bigger than 0. So maybe 0 0.1, 0 0.01, 0 0.001. Let's try to see what's happening with our calculator. So arctan. So arctan is the same thing as tan inverse, by the way. So tan to the minus 1 of 1 over x. So I'm going to do like shift tan, and that's going to give me that tan inverse. And then I want 1 divided by 0.1, and then we'll see what pops out. So I'm going to get something like 1.47. It's going to take 2 decimal places because I just kind of want an idea of what's happening. So tan inverse of 1 divided by 0.01, that was like 1.56. And let's see, so tan inverse of 1 divided by 0.001. Yeah, like, as again, about 1.56, 1.57. Okay, so it does look like I'm tending towards something. It looks like I'm tending towards, you know, this 1.57-ish region. And I believe arctan has some interesting things happening as vertical asymptotes. So something tells me we're probably tending towards a vertical asymptote for arctan, which is pi by 2. So let's take pi by 2 and see what we get as a decimal number. And that is about 1.57. So my guess is as we're getting closer and closer to 0 from the right, this limit is tending towards positive pi by 2. So it's tending towards arctan's horizontal asymptote. So let's repeat the process for values that are a little bit smaller than 0. So maybe like negative 0.9, negative 0.99, negative 0.999. And we'll see what's happening with the arctan function over on the other side. So I get negative 0.84. And like 0.79 negative. Then again, it's pretty close to 7.9 when I do some rounding. So it's like 7.85. So again, it does look like it's tending towards something. Oh, you know what? I totally am not using the right numbers, am I? Look at this. This is tending towards -1, isn't it? That's getting closer to -1. So I want to actually get closer to 0. So I totally like fucked up here. I blame the wine, but it's just an oversight on my part. So maybe let's pick better values. So what is actually tending towards 0? Like what's super close to 0? I guess it would be this, wouldn't it? Like these numbers would be getting closer and closer to 0. That feels super awkward, but I think that's the way to go here. And that's actually going to give us the values that we want. So this is actually come out as -1.47, I think, -1.56, and negative like 1.57. So we're going to get pretty close to those values that we had before. I'm just going to double check and make sure that's true. Yeah. And that makes a bit more sense in my head because, again, I notice this is pretty close to -π/2, which is the other horizontal asymptote that arctan has. So as we get close to 0 from the other side, we're tending towards the other horizontal asymptote, which is -π/2. So this overall limit doesn't exist. Holy Hannah, that's a crazy one. I'm actually kind of curious. I want to know what arctan... Will Desmos even let me plot that? Desmos must let me plot this. I'm so curious. Yeah, tan inverse of 1/x. Yeah, show me what that looks like. Really? Is that it? Wow, that's not as exciting. I was hoping that it would be more exciting than this. That's super not exciting. Oh, man. But there it is. Yeah, as I get closer to 0, I'm getting closer to, you know, that -1.57. And as I get closer to 0 from this side, it's tending towards positive π/2. That's crazy. Okay, cool. I never knew what that function looked like. All right, so there is the work. I mean, a chart or a table here is probably the easiest way to try to figure this one out. Okay, last question on the docket for today is 7e from the practice test, and that is the limit as x tends towards π/2 from the left of ln of cosine of x. Again, this looks particularly not pleasant at all. So let me pause for a second and have some wine. Oh my goodness, how are we going to do this? Maybe we can work with the cosine part first. So maybe I can work just with this, and I can figure out what's happening with cosine as I get close to π/2 from the left. And then maybe that'll tell me what's happening with the natural logarithm function as I'm getting close to π/2 from the left. So I'm actually going to draw the cosine function. So my cosine function looks something like this between 0 and 2π. So here's π/2. And we're approaching pi by 2 from the left-hand side. So we're coming in this way. And it would appear, based on the picture that we have here, that the y value that we're going to get as we get closer to pi by 2 is 0. So my guess is that this inside piece is getting closer and closer to 0. I'm not going to say it's equal to 0, because that's not going to happen, but it's getting closer to 0. And it's always going to be a positive value. And I'm saying positive because if I had approached 0 from this side, I'm always going to have a negative y sequence as I tend towards 0. But over on this side, I have a positive y sequence. So that's going to give me some information about maybe what's happening with my natural logarithm function. So what happens to the natural log of x as x gets closer to 0 from the positive direction? Well, again, we can plot the natural logarithm function, know what that looks like. And as we get closer and closer to 0 from the positive direction, it looks like my y sequence is getting larger and larger negatively. So it looks like this is tending towards negative infinity. So I think overall there's a vertical asymptote happening with this particular function. I think it's tending towards negative infinity. So here's my summary thought process on this one. So the limit as x tends towards pi by 2 from the left of ln of cosine of x. So as x approaches pi by 2 from the left, we know that cosine of x approaches 0 from a positive direction. Okay, so I know what's happening to the inside piece. And as cosine of x tends towards 0 from the positive direction, my ln of cosine of x will tend towards negative infinity. Okay, so I think I'm okay saying that this limit doesn't exist, but it is getting really, really big in a negative direction. So let's take a peek at this on Desmos just to see if we are correct. So ln of cosine of x. That's interesting. And we were looking at, what, pi by 2? Okay, so pi by 2 does look like it is indeed an asymptote here. Yeah, and as we get closer and closer to pi by 2 from the right side, let's put a slider in here so you can kind of see what I'm thinking. So as I'm getting closer and closer to pi by 2, it looks like my y sequence is going to get big and negative really, really fast. Okay, so that's that green dot. Cool. And those are some kind of intense limits. And I'm not going to lie, I don't think the limits on your midterm are quite as intense as these last two limits that we worked through. So if you're able to kind of follow these last two limits, that's great. I think 7D is hopefully fairly accessible because all we have to do here is do a chart. 7E you can kind of reason through as long as you know what the functions look like. If you don't know what the functions look like, you can always try a chart here as well. You only have to do 1/2 of the chart. And hopefully you can get that information that the y sequence is getting really, really big and negative. I'm just going to quickly check. Let's see. I don't think I have any other things in the inbox. So I've covered, I think, everybody's question. They have a squeeze theorem question. What do we want to do? Oh, I actually have one more question here to do from the textbook. So So if you do have any last minute questions popping in, just toss them up into the chat. So I do have the textbook here, so if you have like a textbook number or something I want to work through, just let me know, page and question number. I'm going to copy down, this looks like question 3. What page would that be on? It's 2.8. Yeah, so I'm on page 161 and number 3. So I need to plot a couple of functions for you. I'm going to do that in some different colors. Let's see, we've got 4 functions. So we had 4 functions given to us in blue, and we want to try to match them up with their derivatives, which are given in red. Okay, so we got a nice parabola. Okay. So, can we do this? I think we have the power to do this. Okay, so what information do we know? Oh, the functions are given in blue. And the derivatives of these 4 functions are given in red. And the goal is to match them up. All right, so I'm just going to move over to maybe a green marker here. And there's one that's super obvious to me right away. I do believe that this function here is going to match up with this derivative here. Now I can try to give you some reasoning here as to why that might be the case. The first thing that kind of pops out to me is I have 2 corner points. So I have 2 points on this original function where I'm not going to be able to find the derivative. And that kind of translates over here as kind of gaps in my derivative function. So that's why these 2 are going to get matched up. So those corner points are going to get matched up to this red function that has some spaces. Okay, so after that, I'm not sure that anything else is super obvious of what it should be. So maybe let's draw a couple tangent lines. So I'm going to pick a different color here, maybe in purple. What, is this like a rainbow color? What the hell? Can I really do rainbow colored? What? That's crazy. Okay, I'm not going to do that because that'll be weird. Well, I'll pick just a straight up color. Maybe I'll do purple. I'm going to draw a couple tangent lines. So let's look at, there's a tangent line here and a tangent line here that are going to be equal to 0. Same with this one. It's going to have 3 tangent lines that are equal to 0 here, here, and here. And on this last blue function, it looks like I'm going to have just 1 tangent line that has a slope that's equal to 0. Okay, so I'm specifically looking at slopes that are equal to 0. For my tangent lines. And I think that might be enough information for us to finish this up. So take a peek at this. This one crosses the x-axis once. This one crosses the x-axis twice. This derivative crosses the x-axis 3 times. So that seems suspicious to me. So I might match up this function with this function, with its derivative. Okay, because there's one place where my tangent line slope is 0, and there's one place where my derivative crosses the x-axis. This one would then naturally get matched up with the parabola, again, because I have 2 tangent slopes that are equal to 0, and 2 places where I cross the x-axis, which is going to leave one more pairing of these 2 functions over here. Okay, so that would be my guess on how these are matched up, kind of based on some information that we do know about tangent lines and tangent line slopes. Stuff like this, kind of more geometrical applications of kind of matching up functions with derivatives, that's going to come up a little bit later. So, I mean, if you can't really follow my argument here, it's not a huge deal for test number 1, because we're going to explore this a little bit more coming up in the next couple weeks. If you are able to follow the explanation, then that's great. That means you're kind of ready to go for the next stuff that we're going to be talking about. Essentially, we're trying to figure out what we can learn from our original function and our derivative. So what kind of information can I pull together about the derivative that tells me some info about the original function and vice versa. So that'll be kind of after the midterm. But a cool question nonetheless. Yeah, so I will chill out here for a few minutes and kind of finish off my wine. No one's really chatting about anything on the chat, so I mean, I am happy kind of ending it here if you are happy ending it here. But if you do have some other questions, I mean, feel free to send them on. Otherwise, I will see everybody tomorrow morning. Such a good wine. Oh yeah, no problem, Ali. I'm glad. Hopefully it made sense. And yeah, if you do have any questions about kind of those last two, I think they're a bit tricky. Are they kind of realistic for our test? I mean, 7E is probably pushing it to the limit. I mean, I would. That was a really bad pun. I'm sorry. So yeah, 7E is pretty tough. And same with 7D is pretty tough too. But I would say, like, if you run into a limit and you're not really sure what to do, then kind of your last resort is to go to the chart. So make yourself a table and see if you can kind of figure out what's happening using the table. I would say that's kind of your last ditch effort if you can't do it algebraically. But of course, you know, we've seen algebraic is typically the way to go if you want to kind of a smooth and easy ride to a final answer. All right, so nothing specific popping up in the email, nothing popping up in the chat. So I just kind of assume that you guys are good to go and there's nothing else that you want me to review. So I will be signing off to grab some dinner, and yeah, I'll see everyone tomorrow morning.